Something going on in the chat. Let me see. Skipping class is against my nature and a waste of money. Yeah, that's true. And showing up is like 80 to 90% of success in life. So good on you. I was wondering if anyone has heard about the abandoned oil tanker off the coast of Trinidad that's about to sink. I was curious because we're talking about climate change and it's on the verge of spilling 1.3 million barrels of oil in the Caribbean. I did hear about a stranded tanker and then I forgot about it. Huh. Yeah. Have a look at that and tell me more about it Friday. I brought up the tanker the first day we talked about oil, but I don't know if anyone saw the message. Well, sorry, Allie. Yeah. Oh, where's this dog? I don't see. Oh, there she is. Yeah, puppy. All right, it's 2:00 and we're almost at halfway participation. Great. Okay, speaking of participation, I want to show you the schedule really quick so you know where we've come from and where we're going, and an important date next Monday to pay attention to. So I'll stop sharing this screen and share the schedule. All right, here it is. Yeah, so even though we're only on week 5, we're over halfway through because there's a lot of days off in the remainder of the quarter. Veterans Day, and then Thanksgiving break. And then the last week of class will be listening to each other's podcasts and voting on them. So not a whole lot of lecture left. The date I want you to pay attention to is next Monday, November 2nd. That's the podcast project description day. And so we're gonna get project ideas motivated from the book Drawdown. It's actually a living document that's continuously updated on the web, and it's identifies like 100 different climate mitigation strategies. And you can choose to do a podcast with your group on one of those mitigation strategies. We'll talk about podcast groups on Monday as well. I'll briefly mention it next lecture Friday to do an announcement. You don't have to do a climate mitigation strategy. You can do any topic of your choice related to climate and energy. But the point is, show up on Zoom Monday to make sure that you get assigned to a decent group. You're welcome to start figuring out your groups now. But if you don't know what your group is, if you show up Monday, you'll be able to find a group, and it'll be with good students. In general, the students that don't show up at all might not be the best group members, just to grossly generalize things. All right, so today we're going to talk about climate mitigation strategies. And then Friday, we'll have a study session for the climate homework, which is due Monday, November 2nd. This one's an easy homework after the midterm, but we'll still do a study session for about half Friday's lecture, and then we'll talk about the scientific method, because it's important to know that climate change is a real thing. It's not a belief. It's not a faith-based endeavor. It is something that you can test, observe over and over and over again. And so to understand the toolkit that is the scientific method that's been established over the last 300 to 500 years, I think is very important for a 101 class. Cool. So show up Monday is the main thing I want you to hear from that whole last 2 minutes. And I'll make a course announcement to remind you all. This will be my second podcast on the context of climate. Well, I think it's pretty important. So good on you. All right, PowerPoint slideshow. Is this showing up? Can't tell what I'm sharing anymore. Share screen, PowerPoint, share. Get the chat back open. Cool. Y'all can see the slides? Great. So we're going to talk about climate change, risk, and response. Most of this lecture is pulled directly from the IPCC, the Intergovernmental Panel for Climate Change, Working Group 2 from the Assessment Report 5, which again is starting to become dated. The next one's supposed to come out next year, AR6. And again, the IPCC is a collection of hundreds of scientists from nations all over the world that convene regularly to discuss the the tragedy of the commons that is climate change. We are all partially responsible for it. Some of us much more than others, but we are all going to suffer from it. Some of us much more than others, and so it's going to take the entire globe working together to solve this. All right, so 3 strategies to treat long-term problems, not just climate change. So let's think of, you all are young, so I can't talk about like heart disease or something like that. Cavities, tooth decay. What are 3 strategies to treat tooth decay? Prevention? Yeah, so that's like dental hygiene. That would fall under prevention as well. Brush and floss, that's prevention. So that's keeping your teeth clean. Filling, so that's not prevention. Damage is already done there, right? No sugary foods, that'd be prevention. Capping the tooth, getting tooth pulled. Yeah, so these are all adaptations. So the damage is already done, so now we will adapt to that damage. We'll get a filling, we'll get our tooth cap, crown, whatever. I got a gold tooth back here. It's pretty awesome. I can trade it for, I can get out of like jail in some crazy place, I guess, if I give them my gold tooth. Yeah. So it's a little different with tooth decay, but so prevention would be all these things that we mentioned. Adaptation would be getting your teeth fixed. And then there's this final one, which is called corrective behavior. So maybe you didn't have the best dental hygiene, but now you've learned your lesson, and now you will start brushing, flossing, avoiding sugary foods. And this would be corrective action. So with a long-term problem, you can prevent, you can adapt, and you can correct. Or you can do nothing at all. Then you just suffer the consequences directly. And you can do all these three things to different degrees, and then have different varying degrees of success with the problem. Yeah, some people refuse to make these changes. Yeah, it's all over the place, especially with addictions, right? Gambling, smoking, alcohol, drugs. Prevention would be just don't involve yourself. I don't know what adaptation would be exactly. Maybe Nicorette gum or something. And then correction would be something like smoking cessation. So there's all sorts of systemic long-term problems, and they all have these 3 qualities to them for removing the problem. The tricky thing with climate change is it's a collective problem. So someone's individual behavior won't make that big of a difference, if any difference at all. And so we have to work together, and those are much, much trickier to deal with. There is a economic philosophy treatise called The Tragedy of the Commons, written in England, I don't know, some 300 years ago. I forget who wrote it. Basically talking about these sheep fields that were grazed by communities, and each shepherd could put a certain number of sheep on the field, and the field would be sustainable. It would grow grass each year and feed the sheep. The problem is you get more money if you have more sheep, because then you can sell more wool. And so shepherds were putting more and more sheep, and they were getting theirs at cost to the field, at cost to the commons. And the only way for it to be successful is if all the shepherds work together and have a quota for the number of sheep they'll place on the field, on the commons. But of course, that's hard to do, because people are selfish, people cheat. People have extenuating circumstances. I need to do this right now, and then I'll be better later, that sort of thing. And so these shared problems are really sticky. And we have a massive one right now, which is climate change. I guess we have 2, right? The coronavirus is obviously a huge shared problem too. If we all do the right thing and wear a mask and socially distant and wash our hands, then it will go away. It's clearly evident in places like New Zealand, even smaller communities in America, like Vermont, for example. But if we are selfish, or, have bizarre ideological
Just
Whereas,
stubborn?
yeah, bizarre ideological constructs, like we conflate freedom with, putting the mask below our nose for some reason. Where's Vermont? Vermont is about 5 hours northwest of New York City and even closer to Boston. So it was near these big corona outbreak centers, and they didn't suffer the consequences because they shut down. They require people to quarantine if you visit Vermont. Yeah. And Tony mentioned Vermont caseload is now growing, granted from a low starting point. Yeah. So coronavirus is certainly a shared problem, as is climate change. Okay, so the strategies to treat systemic problems are prevention, adaptation, and correction. This is a lot easier for an individual problem. It's still a challenge, but at least the onus is on you and you can choose to fail or succeed. It's much more difficult when it's shared because you can do the right thing, but you still have to rely on your neighbors to do the right thing. Already talked about tragedy of the commons. Prevention works well for individual problems, but not as well for shared problems. Okay. So what are some mitigation strategies to climate change? I briefly flashed them.
What's a mitigation strategy?
It'd be like a good question. It'd be either an adaptation or a correction, or even prevention. Mitigation strategy is prevention, adaptation, or correction. It's the broad envelope of those three categories. Taxes on carbon emissions, yes. So that is a policy strategy which would then punish the emission of carbon dioxide, and so it would become financially painful to emit carbon, and so that would lower carbon emissions. So that would be correction. More efficient electric cars. So that would be prevention. So we're not even emitting as much carbon, and we have the same energy service, i.e. transportation. Using renewables, that would be prevention. We're providing energy without as much carbon. Geoengineering, that would be correction, I suppose. Or yeah, that's correction, because that's kind of like getting a filling, right? You're planting more trees, that would be adaptation or correction. So emitting the same amount of carbon, but now we're drawing the carbon down. So same with carbon sinks. Carbon capture and sequestration would be a corrective action. So yeah, we have all these different strategies. They're categorized here in different broad energy use categories, I should say. And so we have things like efficiency and conservation. So increasing transportation of cars, reducing miles traveled. Where did it go? Increasing building efficiency. So that's things like insulating your buildings, changing your lighting, changing the way you heat your building and the water in your building. Increased efficiency of electricity production. So you can make your buildings as good as you possibly can, but if you're still getting electricity from a dirty source or inefficient source, then you're only halfway there. So first electrify everything, make it as efficient as possible, and then make the electricity as clean as possible, or do it in tandem. Carbon cap, electric transportation, people are mentioning. There's somebody mentions in the chat, there's a building in the city I lived in that was a gold level green building. There's a few completely carbon neutral buildings in Bellingham, various homeowners that have taken a passion to this. If you take my carbon greenhouse mitigation class, or even the Northwest energy production class, it's a field course. We visit some of those homes. There's a building in Seattle called the Bullitt Center, which is a quote unquote living building. It makes more water than it takes in. It pulls more carbon in than it emits. It makes more electricity than it requires. And it's supposed to be a living building and definitely sustainable. They even take all the human waste and turn it into dirt, an age-old tradition that we've forgotten how to do in the last couple hundred years. All right, I'm not going to read all these, but these are different mitigation strategies for climate change. So that's half the story. So what causes a problem? like tooth decay or climate change, how do we stop it? We can correct, we can prevent, we can adapt. But the problem's here. It's here already. It's causing issues throughout the globe, and the degree in which societies suffer from climate change depends on their components to risk. So there are, just as there are three principal aspects of systemic problems, there are three principal components to risk. And so let's use an example. We'll do two examples. I think coronavirus is so appropriately mapped to climate change. But let's start off with an easier one. Maybe this doesn't even make sense because nobody's been on campus. But imagine, if you will, it was normal times and we were on campus and walking through Red Square on a daily basis or even a nightly basis. So what are the components or factors leading to the risk that you will trip walking through Red Square this week? And imagine it's the before time, before coronavirus. Yeah, loose brick every time. Yeah, so there's loose bricks all over there. So that's one component. It falls under slipping on leaves, structural design, light level, loose bricks, rain. So these are all, oh, except for looking at your phone. That's the unique one. Stepping on your coat, that's kind of a unique one as well. Slipping on black ice. So excessive drinking, yes. How much have you partied that night? That's going to make a huge difference. So most all of these so far, like loose bricks, leaves, ice, rain, this is an external hazard. It's something that has nothing to do with you. It's just the way Red Square has presented herself. Drinking or stepping on your coat or looking at your phone, that has something to do with you. So that's your vulnerability, whether self-imposed or imposed based on the society that you live in. Other people, that would fall into hazard, right? There's always that guy going too fast on like a Razor scooter, or now there's like e-bikes bombing through there. Sorry, that's sometimes me with my little girl on the back of it. Yeah, or the dude in Heelys. Are those still a thing? Too clumsy, so that's on you. So far we've captured two of them: external hazards and internal vulnerability. So your risk of tripping on Red Square has something to do with Red Square and something to do with you. There's one final thing. And it has to do with statistics, right? If you're in Red Square a lot more, are you more likely to trip there? What if you never have been to Red Square in your life? What if you're one of these Corona freshmen and you're still, on Bainbridge Island in your parents' beautiful home or something? What is the likelihood that you'll trip at Red Square? 0% chance. Yeah. So the final component, there's vulnerability, that's on you. Hazard, that's on the external conditions. And then the final one is exposure. How often you see that risk, how often you're in Red Square. So we can map those three components to risk to climate change. So assessing climate risk and impact. Here's the central risk. There's hazards, that's external, vulnerability, and exposure. So let's look at Bellingham in terms of climate change. The hazard to us is not that severe. We are in a temperate climate that's totally mitigated by being right on the Salish Sea. And so it never gets too hot, never too cold here. And it won't change for a long time because we have this huge thermal sink. Water has a big heat capacity and we're surrounded by water. We're not susceptible to drought. I mean, yes, I've heard people say that we're experiencing a drought year here in Whatcom County or something in the years past, coming from California, maybe like this, we're fine. This place is too wet. Maybe I'm speaking out of turn here, but it seems like there's plenty of water to go around. Um, Rivers are flowing. We have big snowpacks. We have glaciers. There's water. Uh, there is a slight hazard with things of, forest fires, but it seems like forest management is pretty good in the immediate vicinity to Bellingham as well. So our hazards from climate change are pretty low. There may be hazards to our economy if fisheries fall apart, things of that nature. But in general, Bellingham's pretty low hazard. Our vulnerability is pretty low too because we're relatively well off. Standard of living, GDP in Bellingham is high. Mean income is high. Yes, it's largely unaffordable to people in your demographic, young people. But in general, like there's money in Bellingham, and so we're not that vulnerable to climate risks either. We'll be able to adapt. And then finally, exposure. Again, being at the 49th parallel, near the ocean or near the sea, we're not exposed to the largest risks from climate change. We're not going to experience desertification, sea level rise. I don't know what it's going to do. Take out that the acid ball or something. It's not that big a deal here. So I got a question in the chat. Why do you think at Western we care so much about climate risk if we have so little impact from it? Is it just because that Western people are the best? Yeah, I think you answered your own question. No, we, in a certain degree, comfort and affluence, and again, I'm using affluence in a broad term, not pure net worth term, allows you the luxury of thinking about big problems and caring for other people. It's kind of like Maslow's hierarchy of needs. If you have food, water, and shelter, you can start thinking about others. You're able to provide for others. So I think that's part of it. I think that people at Western in general really love the outdoors. We have so many opportunities to enjoy the outdoors here, and so we're more aware of it than if we were living in an urban hellscape, for example. And yeah, somebody mentioned awareness and education. Yeah, we're very educated here in this population. And many of us may have come from somewhere else, and we're aware of places that are more vulnerable and more exposed to climate risks. So that's Bellingham. There are places that are nearly so fortunate for one, two, or all three of these categories. Do any of you have any ideas for places that are more at risk to climate?
I'm from Los Angeles, and I would hate to see what happened to Los Angeles happen here.
What happened to Los Angeles?
Yeah, with all the trees and the forest fires.
Forest fires. Yeah, Orange County is still on fire right now, and it's almost November.
Yeah, and since I've lived there in Los Angeles, the climate has changed so much from when I was little to now. So,
in what ways? Give us an example. This is really interesting.
Well, when I was growing up, like in the foothills of Southern California, you could go up and it was beautiful. It was green. There was a lot of like rivers, and there was still ice, like snow in the foothills, but there hasn't been snow in years now. It's dry, everything. It's just nasty now. So I've seen the impact from the time I was little to now in Southern California. And I would hate
I
to
lived
see,
in, yeah.
Mhm.
Sorry, go ahead.
Yeah, if that happened here, I would hate that. Yeah, sorry.
Yeah, no, and yeah, maybe I'm being naive or ignorant. Maybe it will happen here. It's just going to be 30, 40, 50 years down the road. I moved up from Northern California, and that was near Salinas Valley, where all your salad is grown here in America. If you eat salad at a restaurant, it came from Salinas. And people down there were joking when I moved up here, saying like, "Oh, you're moving up near Skagit Valley. That will be the Salinas Valley of the 21st century. That will start growing all the lettuce and food." Yeah, it was weird that the last 5 years I was in SF, it just didn't rain. It never rained anymore, and yeah, and then every fall it'd catch on fire. Yeah, so there's different places that have greater risks. Someone mentioned Mauritania. Thank you for that. That's why I introduced that nation in particular. I think there's a lot of nations that will share Mauritania's plight. One of the ones that is at the greatest risk is Bangladesh. It's a very populated country that's on the delta, and so it's very low lying, and it's going to be very susceptible to sea level rise. Many island nations in the South Pacific, Maldives in the Indian Ocean, super susceptible to climate change. And then northern locations or Arctic locations are very, very susceptible to climate change because of sea level rise, permafrost loss, and lack of ice. And so a lot of the transportation was just done on frozen water. And if the frozen water isn't there anymore, it's going to be devastating. And then longer term, things like breaking down the thermohaline cycle that we talked about last time and plunging Europe into much colder conditions. So it's not like everywhere is going to get hotter. Things are just going to get much more dynamic. And you know this from the first and second law of thermodynamics. Now we just have bigger gradients. And as these gradients get degraded by dissipative structures within the natural Earth system, things are just going to be more chaotic. I mean, we ran out of hurricane names this year, where Hurricane Zeta is headed towards Louisiana, the like third or fourth hurricane headed towards Louisiana this year. It's insane. So I think we are pretty lucky here. At least that's where I put my chips on the table. I was like, yeah, Bellingham looks good. I'm going to move here. But there's a lot of places that are going to suffer. And in particularly, it's the developing world that's going to suffer the most, because they won't have the excess funds, the extra money to adapt. They can't afford the filling. They can't afford the crown or the gold tooth. And so they'll just suffer with it. All right. So IPCC had this risk impact summary. I'm not going to read a wall of text. That's bad lecturing practice, but you can check it out. Basically, there's going to be changes across the board in all locations of the planet, and they'll be different in different places. Some places will suffer drought. Some places will suffer flooding with excess rainfall. Some places will suffer flashier rain. That is actually one worry with Bellingham. Apparently, the Pacific Northwest benefited from this misty rain, so that it allowed for a long time for the soil to saturate with the water. And if that misty rain turns to more torrential rain, stuff that you experience down in Houston, for example, or Bangladesh, then the soil won't have time to soak up that water, and it'll just run off into the sea, and that causes erosion and poor water storage. Forest fires, desertification, all these sorts of things that we've been talking about. And so this cartoony map by the IPCC looks at some of these changes across the globe. I don't think this is terribly useful beyond the fact that it's just saying stuff will change everywhere. These bars indicate their confidence that it's attributable to climate change. These cartoon pictures indicate whether or not it's a physical system, biological system, or human managed system. The solid versus transparent, I have no idea what that means. Minor contribution of climate change versus major contribution of climate change. I tried to figure that out. I read through the report. I like numbers better than these cartoons. But basically, let's look at Bellingham. We're going to have changes to glaciers, snow, permafrost. We'll have changes to water. We'll have changes to fisheries. We'll experience more forest fires. All the sort of stuff you would expect. The scarier ones are things like food production. And so notice in India, sub-Saharan Africa, Europe, Middle East, there'll be big changes in food production, and that will lead to migration, right? It will lead to quote unquote climate refugees. Somebody in the chat asked, what does IPCC stand for? That stands for the Intergovernmental Panel for Climate Change. Again, collection of hundreds of scientists across the globe that try to say, what's causing climate change? What should we do about it? Another chart from their adaptation report is crop yields. This is pretty interesting. So it's showing the percentage change per decade over the 21st century in various crop yields. Basically, it goes down across the board except for soy. And so it's broken down by region, tropical versus temperate versus crop type. So things like wheat, which is a staple in Western societies, and maize, which is a staple in South American and Latin societies, and rice, a staple in Asian societies. All of these are likely to go down. And so food production is going to become more difficult, more challenging in the future. Along those lines, how will it affect other species, not just humans? This is a really interesting plot. It was titled, How Fast Can a Tree Walk? How does a tree walk? How does a tree move over time? Maybe not just one tree. Wind, spreading seeds. Yeah, roots, sort of. Some trees do the root thing. But yeah, tree grows, drops a seed, new tree grows. So it walks very, very slowly. And so this chart shows the maximum speed at which a species can move, kilometers per decade. So this very slow rate of movement. So this is the maximum rate in which they can move. This is median rate. There's black bars, and this would be the quartile range. 20, like the 75th percentile can move this fast. And these lines are different climate change scenarios. We are definitely in the 6 to 8.5 climate model prediction. Remember that graph I showed last time where we're way above the curve? And so this is how fast different species have to be able to migrate to stay within their habitable zone, the zone in which they evolved. And so this is global average, and then this is flat areas. Why do they have to be able to move faster in flat areas versus hilly areas? Any ideas? Less protection, kind of.
Because it takes more energy to get through the hills than on flat areas.
You're getting to it. It's not necessarily more energy. Hills allow more dynamic ecosystems. There you go. Yeah. So you got halfway there, Katie, and then Gavin took it home. So I don't know if any of you have been to Hawaii, but you can choose your climate on Hawaii. If you want it warmer, you just go closer to sea level. If you want it colder, you just go up the Shield volcano. And you can see a lot of farms for different types of crops and different types of animals at different elevations. So the higher you go up, the colder it gets. You know this when you drive up to Mount Baker, for example, it gets colder and colder and colder. And so if it's a hilly area, these trees and animals don't have to migrate as far because they can just go uphill. Speaking in colonial terms, my apologies, but that's why the British, when they invaded India, they settled in New Delhi in the Himalayan steppes rather than down in Mumbai or something, because it's a lot cooler up there, more civilized tea drinking climate. This is how fast these can move. So primates are in trouble, rodents are in trouble, plants, herbaceous plants and trees are in trouble. So these are things that spread by seeds. Herding animals are not in trouble because they migrate, they can move quickly, and carnivores just follow them, so they're not as much in trouble. insects have no data at all. I don't know why that's there. I don't know what's happening there. And then yeah, mollusks. There it is. It's just interesting to think that there'll be obvious losers to climate change in the ecosystem, and that's that tier zoo. It's kind of tongue in cheek, but that video I linked to in last lecture, or tier, forget what it's called. Anyways, it pretends that climate change is a video game, and so which different animals are going to adapt better or not to this new game that we're introducing. Okay, within the assessment report too, which I'll link to in Canvas if I haven't already, I think I may have. This is what you'll do for part of the homework that's due next Monday. And so you'll look at different regions, and they're big continental sized regions, which is a little bit of a disservice because, you know, just thinking about Washington State, we have a bunch of different climates. So if you say something like Africa, like what does that even mean? But they talk about different risks, key risks, adaptation issues, and prospects. So what will allow for success or failure based on the political and societal systems in place in a particular place. Different climate drivers that will be really affected by climate change. And then, yeah, risk and potential for adaptation. So I'll have you all look at these in depth for the homework for, I think, the oceans, and I forget one other region. So this is just a brief introduction to that. We'll talk more about it Friday. All right, and yeah, here's the ocean. So we have to worry about things like acidification, warming. So we've already had changing weather patterns here in the Pacific Northwest due to a warming of the ocean, the so-called blob. Yeah, more stormier storms, rainier rains, just more energy in the system. Okay, we have 15 minutes left. So there's prevention, adaptation, and correction. Let's look at some corrective options. So so-called geoengineering. Humans are crazy. Not only are we the only exosemitic animal, we use energy outside of our own metabolism. We also, another name for humans is Homo faber, the monkey that changes things, that fabricates things. And so we fabricate our shelter, we fabricate our own fur, we fabricate things all around us. And we've gotten so much technological prowess now that we could fabricate the entire planet if we so choose. And so some geoengineering ideas, and most all scientists agree, Union of Concerned Scientists, for example, say that we need to study the system a lot more before we do any of these crazy ideas, but they would technically work. They might work too well, or they might have unintended consequences. A common story in the last 500 years of human innovation is we create new problems while we're solving the old problem, right? But some ideas are carbon dioxide removal. This could include ocean fertilization. Russ George, he is a businessman down in San Francisco, and he wanted to increase salmon yields in the Pacific Northwest, particularly for a tribal village is either in British Columbia or Alaska. Heart was in the right place, and he knew that the salmon relied on algae and phytoplankton, and a limiting agent for phytoplankton and algae production is iron. It's a vitamin they need to grow, and it's limited in the ocean. And so he seeded the ocean, the northeast Pacific Ocean off our coast, with a bunch of iron. Kurt's Gazette just released a video about geoengineering the other day. Awesome. I'll link that. I haven't seen that yet. I like that guy. So he seeded the ocean with a bunch of iron, and it did increase algae production in 2012 and evidently increased salmon yields in 2013. So it worked. And it also pulled a bunch of CO2. The algae pulls a bunch of CO2. He did it without permission. A lot of people got upset about it. But that's one idea. Seed the ocean with iron to increase CO2 sequestration. Planting forests is probably a better, safer idea. So China is doing that in abundance right now. They're planting a tremendous amount of trees. Other ideas are solar radiation management. So either we make the blanket less blankety by removing CO2, or you can make the sun less sunny, and so less energy in the system. So ideas of that are sulfate aerosols into the stratosphere. So sulfate is this very reflective, white, shiny particle. If you put it in the troposphere, which is what we live in, where most of the clouds are and the rain is, it just rain out and fall back to Earth. If you blast it all the way to the stratosphere, it'll stay suspended up there and just reflect more sunlight. It's kind of a decent idea. It won't last forever, which is actually a good thing. So eventually we'll fall out. So if we put too much or something, it'll slowly fall out. But again, unintended consequences, we need to study these things. And the quote that goes over and over and over again is, we should perform the experiment in the laboratory, not at a global scale first, right? We shouldn't just use the Earth as our laboratory. Other ideas: enhanced cloud reflectivity, so cloud seeding, roof whitening, but again, you'd have to cover an area larger than the United States for it to ameliorate all the climate change we've introduced so far. Planting reflective crops, so geoengineering plants that are more reflective, kind of a crazy idea. Solar-based reflectors and shaders, so you can put massive shades in orbit, the same orbit that the moon is in, basically, or a geosynced orbit, or in different Trojan locations. Sorry, I'm digressing. And they'll be stable, and they can reflect sunlight away from the Earth or shade. But again, National Academy of Sciences concludes that deploying geoengineering now would be irrational and irresponsible. We need to study these systems a lot more before we just go crazy, right? Maybe things need to be more dire, but let's not use the crazy radical drugs first. Let's see what ibuprofen does. All right. Geoengineering solutions to climate. So this is a picture of them, like iron fertilization, carbon sequestration, reflective crops, growing more trees. That's the one I like. that seems sensible. Tony writes in chat, how about we just reduce our carbon footprint? Yeah, so that's prevention. Prevention is always the best thing. Stop smoking cigarettes, stop eating sugar, stop drinking booze. These are the obvious things. But if we can't kick the habit, then we have to move to something else. And adaptation would be things like, seawalls, greenhouses, whatever. And then correction would be this more drastic geoengineering type thing. All right. So what's policy's role? We largely have the technical solutions to climate change. That's something that I've been working on with my own research in the last decade or so. And the more and more I've been part of this business, I realize it's a technical problem, but it's also a people problem. I'm now trying to identify and work on technologies that make people's lives better, so they choose to do the right thing because it makes them happier, right? How can we develop climate solutions that actually improve happiness and quality of life so people choose to do it? So it's not like a punishment thing. But I digress. So policy's role is to scope, so identify risk, vulnerabilities, objectives, and then make a decision. Then analyze the success or failure of those decisions, evaluate trade-offs and risks from those decisions, and then implement them, and then see what happens. Review, learn, monitor, collect data, and then see how things have changed, and then rescope, and do this over and over and over again. This involves data collection, observation, scientific method, patience that are longer than 4-year or 2-year political cycles, unfortunately, and cooperation. And so we need smart people, patient people to implement good policy and law, not only in this country, but globally, to make this a success. Capri, work with human nature, not against it. So that's something I'm starting to really try to focus on. How do we make positive climate decisions as easy as walking downhill? All right, ended a little bit early today. which is a rarity. Happy to take questions. I'm going to write down that Kritz Gazette video so I can link that and Climate and in Canvas. And then I'll put the tier zoo up there as well. See, I had some backup slides, blah, blah, stuff is going to get hotter. Yeah, that's it. All right. Any questions, thoughts, comments? Started grading the midterms, looking pretty good so far. Hopefully have those done this weekend.
I had a question about the graphic that was just up on screen, the one about the implementing the methods. I'm just confused about the like pumps liquid CO2 into rocks bit. Like, how would that help? Wouldn't that just delay the problem?
Yeah, it's literally like, you know, someone tells you to clean the living room or something and you just sweep everything under the rug. That's, I guess you shouldn't use the word literally that way. It's figuratively sweeping it under the rug. Interestingly, though, CO2 is stable. I forget at depths beyond 600 meters or 6,000 meters. So if this is the surface of the Earth, if you put it down, I think it's more than 600 meters. The pressure is such that CO2 becomes liquid and it'll just stay down there. And especially if you put it underneath a cap rock. And so where do you identify cap rocks? Where have you heard that phrase before in this class?
Drilling.
Drilling for oil, right? So usually there's gas and oil in good cap rocks that we've identified. 100% of CO2 sequestered thus far is to increase the production of oil and gas. It's called enhanced oil recovery. So you take CO2, you pump it down here, it displaces the oil and gas, and it goes back up here, and you pull it out of the ground. So far we are using CO2, not to sequester it, but to get more oil and gas out of the ground to make more CO2. Cancer for the cure.
I have a question.
Yeah.
Would it take like way too much energy for it to be a good idea to like take CO2 and like turn it into something else like chemically?
Yeah, good question. So CO2 is thermodynamically very downhill. Carbon and oxygen love each other, and so they bind and it releases energy when they create that molecular bond. And so to break that bond back apart takes a lot of energy. But there are many different ideas. So there's using things like wind or solar to break apart carbon and CO2, and then take the carbon and create things like carbon black, which is a very useful component in lithium-ion batteries, printer ink, all sorts of different electronics and various components, paints, dyes, inks. And so carbon black is a very useful thing. But again, it takes energy to break that CO2 apart. One of the ways you can lower that energy is using things called catalysts. They're like enzymes. You have enzymes in your bodies that make it easier to break down fats and sugars and get energy out of it. A catalyst lowers that amount of energy to break something apart due to quantum level effects that are beyond me. But people are developing different solid oxides and different ceramics that act as a catalyst to help break apart the CO2. And then you have some energy input, wind, solar, electricity, et cetera, to drive that catalytic reaction and break the CO2 apart. There's a group in British Columbia that's working, I think, using hydropower and a catalyst to sequester CO2. But again, all of these things take energy, and they take a lot of real estate to build these massive buildings full of catalysts to pull the CO2. All that's expensive to the point where it just makes more sense to use wind and solar energy to make electricity because it's low to zero CO2 rather than use that to pull CO2 out of the atmosphere. But it is an idea, certainly. And there are useful products from carbon black primarily and other forms of carbon. People are making just breaking apart one oxygen to make carbon monoxide, but then they just burn that because it's energetically, it still has chemical exergy, and they burn the carbon monoxide to make CO2 again. But yeah, CO2 is basically all the way thermodynamically downhill, and that's why it comes out of the power plant. There's nothing left to do with it. You already got all the energy by making it. But excellent question. All right. Have a great couple days. See you Friday. We'll have a study session, talk about scientific method. Show up November 2nd, Monday. That's when we do podcast groups and podcast description.
Thank you.
Thank you.
Adios.
Thank you. How big are the podcast groups going to be?
I think there's 85 students. So I was thinking about like 4 or 5 or 6. I like smaller groups better because people actually work. So maybe we'll do 5.
Okay. All right.
Yeah.
Also, I got a question. Because my friend wanted to know, because he's pretty interested in becoming an astrophysicist, and he was just kind of wondering, like, what are the things he should focus on to become one?
Math.
Math.
Yeah.
From like calculus, because like to model.
Yeah, you got to get into Riemann spaces. So that's 3-dimensional topology, because that's how space actually is. It's mapped with gravity, right? Space-time is this curved fabric. And so, yeah, you got to go past calculus, past differential equations, into topology, where you learn Riemann space.
Wait, do you say topology?
Yeah, topology. That's the vector description of n-dimensional space.
Dude.
Yeah, good luck. I tapped out at topology. I was like, I can't handle
this.
Wasn't
topology the last thing you said?
Yeah, I took it when I was a senior and I couldn't handle it, so I quit. But I would have loved to be that smart, but I wasn't.
Yeah.
But yeah, you need math.
What were you saying about with the quantum physics, that they were basically breaking down the atoms in order to kind of create a catalyst or something?
Oh, the catalytic. Yeah. So, so the way molecules work is they share electrons, and first those electrons repel each other because it's 2 negative charges.
Yeah.
And so they bounce off each other. But when they share electrons, their energy state is actually lower, and it releases energy to the environment via light and heat. That's what happens when you burn carbon. So
it's like
the carbon in wood on a tree, it's fine, right? It's not on fire. You have to jiggle that carbon and in the presence of oxygen in the atmosphere enough that it overcomes that electron resistance, and you make them jiggle fast by putting a heat source underneath them. And once they jiggle enough, they'll get close enough together that they will now see each other's nucleus, which is full of protons, positively charged. And then those 2, or in the case of CO2, those 3 nuclei will then all share electrons together and have a lower energetic state and release that energy to the environment as more heat. And so in the case of burning wood, you have to jiggle them enough to allow them to see each other, and then they'll bond. You can do things. Catalysts are different services of other atoms that won't ultimately be part of that reaction, but it may draw those electrons in a certain direction or a different polarity, such that less energy is needed for those carbons and oxygens to all of a sudden want to bond each other. And so you don't need as much energy input for them to fall. And again, that's the extent of my understanding of it. But you can also use other catalysts in the opposite direction, where, so then to break CO2 apart or any other sort of molecules, you need to put energy into that system to pop them apart. And the amount of energy to pop them apart can be lowered if you change the electron cloud in such a way that they'll freely disassociate. With less of an energy input. So you're lowering the activation energy for that chemical change, that molecular change. I don't know how it works.
Yeah, I don't know either.
It's something you could study. I'm sure it's something I could figure out. I don't know. I like the more big picture stuff rather than that real minutia stuff. Astrophysics rad though. That's as big as it gets.
Yeah.
I could do high energy astrophysics. That's like X-rays, quasars, pulsars, those sort of things. But as soon as you get to black holes, which is the really interesting stuff, then yeah, you need to know topology and Riemann spaces. And I got too stupid.
Yeah. I was reading a book. I forgot. I don't think it's the first 3 minutes of the universe, but it was like a different book. And it was just talking about black holes, and I was just trying to get my head around the concept of the black holes and how it could have like an infinite diameter, but like I don't know, it was just like super hard to wrap my mind around it.
Yeah, it's just because space gets completely warped.
Yeah. But it's like super cool.
Yeah, no, it's fascinating, and I find it really comforting. It makes when I think about that stuff, the trials and tribulations of my own life become kind of like quaint and silly.
Yeah, it's like nice to like kind of break away from like kind of thinking about society and everything, and just kind of get down to it more.
Yeah, and just like, oh, I'm just this lucky collection of energy and matter that gets to, sit on a crazy spinning rock in space for 80 years. Cool, I'll take it. Sounds like fun. Yeah. All right, I'm gonna go.
All right, thank you. Bye.
Yep.